Herd immunity is one of the more misunderstood concepts that's been floating around during the COVID-19 pandemic, so I aim to explain it in this brief talk. First of all, a bit of terminology. R0 is something you may have heard of. That is the number you'd expect one individual to infect. So for instance, if R0 is 2.5, if the first 100 people who are infected pass it on at that rate, then you'd expect the second round to have 250, and this applies at the start when no one else an infected person encounters is already infected, and you're only counting one layer on from there, not any subsequent infections, and that's the basic reproduction number. Another number often confused with that is just plain R, or R subscript T, where the T stands for time. It's also the number you expect one individual who's infected to pass it on to, but that's at a given time as the disease progresses. So as time goes on, you become less and less likely to encounter only people who've not previously been infected if you catch it yourself. So you'd expect RT over time to start getting smaller, but at the beginning RT and R0 are the same thing, and RT is the effective reproduction number. So on then to herd immunity, the subject of this talk. That's the fraction of the population where RT is equal to 1. In other words, if you are infected, you expect to pass it on to exactly one other person, and so new infection stabilize at that level, and it will fairly rapidly reduce because you start running out of new people to infect, and RT gets below 1. You can find these and other definitions at this website, which is a good place to just find this kind of information. So what does R0 depend on? It's the disease itself and the population. So in terms of the disease, it's how contagious it is and how long an individual is contagious. But the population aspects are where the biggest variables are, because they're factors like how dense the population is, how much social mixing there is, and all kinds of other factors. So R0 can vary quite a lot. 2.5 is the value you most often see quoted, but it can be less and it can be more. So onto herd immunity and the big misconceptions around it. If you're already at that level of people who've been infected, when a new outbreak occurs, then you will expect it to be suppressed fast. And vaccines work well if you can vaccinate at around the herd immunity level, or better still, even more. But if the number of infections is rising rapidly, herd immunity doesn't stop new infections fast enough, you get a thing called overshoot. So if you've got a relatively high value of R0, natural herd immunity is not a great plan, particularly if the disease causes a significant number of fatalities, which is the case here. So why do non-pharmaceutical interventions like distancing, masks, and more extreme ones like lockdowns matter? Well, you've often heard the term flattening the curve, and that's also pretty widely misunderstood. It's not just about slowing the pace to avoid overwhelming hospitals, but also you can reduce the total number who get infected and the total number of fatalities, particularly by reducing the overshoot factor if you do get to the point of herd immunity. So let's look now at a simplified simulation. It's a model based on dividing the population 4 ways: susceptible, those who have not previously been infected; exposed, those who are infected but not yet contagious; the infected group are those who are both infected and contagious; and recovered, which a bit perversely maybe also includes those who've died, but the point is it is the category of population who are not passing it on anymore. And fatalities in this particular simulation are not modeled at all, and has many variations you can play with, and has a nice simple web interface, and has the benefit of having been created by a real epidemiologist. So let's have a look at this simulation. Note that here they label what I call RT as plain R, and that it is the same as R0 at the beginning. R0 is set by a bunch of sliders a bit higher up on the leftmost panel that change how fast it spreads. It's configured to 2.5, which is a reasonable value if you don't know anything about the particular society. So at the start, 0.01% are infectious, and nobody is in the exposed or susceptible or recovered states. So R T and R0 start out the same thing, the presumption that everyone who is infectious is only going to encounter other people not, because it's such a low fraction of the population. So let's run the simulation. I'll let it run fairly quickly. And what you see is that the number infected and exposed increase fairly quickly up to a point where it starts to decline. That point is at the stage when the total number who are infected and have recovered has reached herd immunity, which is the horizontal dotted line at 60%. But note that the number who get infected still keeps increasing, even though it's at a rapidly falling rate. And at the end of the simulation, the big takeaway here is that nearly 90% of the population had been infected. So the herd immunity level at 60% doesn't really save you. You still end up with a very large fraction of the population infected. So how does herd immunity help? Well, it's not going to help much if you're hoping that you can just let it contain the spread if you don't do anything else. Flattening the curve will get us closer to stopping at that point, but it's really only a useful concept if you have vaccination as an option. So if you vaccinate at least 60% of the population, if R0 started out at 2.5, then that is going to stop it from spreading fast. But without vaccination, it's not a great help.